Hello everybody and welcome back to this channel where we do super interesting coding projects all of the time. And today we're going to have a look at elastic collisions. We're going to simulate such an elastic collision situation scenario ourselves in C. It's going to look like this. This right here is a Wikipedia article on elastic collisions, and basically it's just circles bouncing around on the screen and colliding into each other, reflecting off the walls, and of course also reflecting from each other upon collision. All right, so we're going to do a lot of graphics programming, but then the tricky part, in my opinion, is to figure out the right angles at which to reflect two colliding circles upon collision. That requires a bit of geometry and a tiny bit of physics. Everybody who's a major in physics or mathematics or so will laugh at me right now, but yeah, I don't care. We're going to just have fun coding. So let's start. I'm going to create a file that's called collisions.c, and let's include. We're going to do all of that using raylib. To do that, we are going to include raylib just like that, and we're also going to need some standard libraries such as standardlib.h. No, I don't even know about standardlib, honestly. Do we need standardlib? I don't know. Standard.io doesn't harm to be included. And we're going to have a main method that opens a window. And let's save some time. Every raylib project always starts in the exact same fashion. So we can go to raylib on GitHub, and on the GitHub page, there's already a basic example. This is a starting example that we can already actually copy. No, so let me just delete my code and paste the basic example. And now let's build from that. So what is this example doing? This is just a main method. Oh God, what the hell did I do? This is just a main method right here. It opens a window, and then while the application is running, something is being drawn onto the screen. So let's just try to run this basic example and then build on top of it. All right, so this is now our collisions directory right here. And to compile this, we have to look up working on GNU Linux in my case. If you are on a different operating system yet, then you have to look up how to do it in your case, of course. And then there's a section on the simplest possible build command. We can just copy that, paste it, and our file is not called game.c, but collisions.c. And then there's just one more tiny difference that I want to introduce. I want to call the output file collisions, otherwise it would be called a.out, which I always find quite ugly. Then I'm going to enable all warnings, extra warnings, and debug flags just in case. And that should be it. And right, it compiled. So for everybody who couldn't see that because my webcam obstructed the view, this is the compilation command. All right, and then I'm also going to concatenate this compilation command with a double ampersand and execute right away, such that every time when we introduce a code change, we can compile and execute the application in one go. And as you can see now, executing this, we get this small little window with a hint of a gray font that tells us, congrats, you created your first window. Okay, so now we are pro graphics programmers, we are completely prepared. So let's adapt this a bit and introduce width and height variables here, or constants, and let's adapt the window title. Let's call it collision or particle simulation. Maybe particle collision simulation. No, particle simulation is fine. And then let's define width as 900 here and height as 600. Then we're going to simulate a bunch of particles. We can also already define how many. The number of particles at first is going to be, should we start with 100 or is that maybe too many? Let's start with 10 or 15 particles at first. And then in the end, we can have a look at how many particles look like if we increment the number. All right. So the other thing that I don't like is the white background. I am going to replace it with black, and then I don't need a text here. And also one small detail that I want to change now is that currently we have this window running. If I look at the system monitor, this is like the task manager in Windows, then we see that the CPU utilization of this application is very, very high. I don't know if we look at the processes currently running, then Collision is consuming 8% of CPU, and that is because I have 12 CPU cores, which effectively means that one CPU core is running at 100% utilization. Yeah, and that is not good. How do we fix it? Well, the core reason is that this while loop is running at full speed all of the time, and we need to throttle the frames per second. And we can do that by calling set target frames per second. I'll show you in a second where that comes from, because I'm not inventing all of those calls. Now we still have a black window, but if we switch to the system monitor again, then you can see that the resource consumption now is much lower. And if we switch to the processes, then there's the collision process running, and it's just consuming 0.47% of the total CPU. Yeah, much better. All right, so now we have already fixed the energy consumption of this program. And we are ready to do some real logic. So what do we need to do? We want to simulate particles. That necessitates that we are able to draw some particles or visualize something first. So how do we visualize something? In Raylib, the practice is always to look up the Raylib cheat sheet. Let's have a look. There it is. It is available under raylib.com. And this is basically Raylib's entire documentation. So Raylib consists of a bunch, I would estimate 100, 200 or 300 API methods. No idea how many there are. And so there's a bunch of API methods, and they are supposed to be self-explanatory. And now let's try to draw a circle. Let's search for draw circle, and there we go. There's a function draw circle, and we can draw a circle based on center X, center Y, radius, and color. So let's do that. Draw circle, center X. Let's just put that at the center of the screen. Width divided by 2. Center Y is height divided by 2. Radius is 40 and color is white. I don't even know if white exists. Yes, it does. Okay. So it's defined in Raylib. Perfect. That's how we do a single circle, and everything else is just building on top of that. So what's the difference between a circle and a particle? Well, a circle is just a static representation of a geometric circle. A particle is, of course, something that's physical, a physical entity that moves across the screen. So a particle, we can define it as, let's define it, type def particle. And as opposed to a circle, a particle also has X and Y coordinates, but I would say they are floating point numbers because we have to, we want to be better than pixel precision when calculating collisions and all of that stuff. So let's add X and Y coordinates, then a radius. We could also introduce a mass, but in this simulation, we're going to assume that all particles have the same mass. This also makes some calculations much, much easier. So we have an X and Y coordinate and a radius. This is basically the exact same definition as a circle, but now comes what the difference. It's moving. So a particle has Vx and Vy properties. And I think that's it. And this is also a small difference. A circle right here, this is a circle in the representation domain. It also has a color. A particle is just a physical object. It does not necessarily have a color. That's something that we can define, that we can decide on arbitrarily then. So instead of drawing a circle, how about we draw a particle now? We draw a particle, and that particle is passed into that method here. So we can create a particle here. Particle is equal to x and y. Let's say 300, 300. Then radius is, let's make it a bit bigger, 50. And then let's give it a speed. And let me just put 2 and 2 here. So that should be 2 pixels per frame. Yeah, we will see. Okay. So this is the particle. That's the full particle definition. And now we need a new method. Void draw particle. And draw particle takes as input a particle, ideally a pointer in my opinion, because we should run the code, we should perform the logic on shared memory. We should not copy a particle into the method. That's a performance improvement. So let's just do this particle right here. Then also down here, instead of passing the particle and then having it copied, let's pass the address of the particle such that it's passed by reference. And then inside draw particle, we can do draw circle, because now we just want to draw a circle, right? Draw circle at particle x, particle y, particle radius, and color white. I think that's already it. Because we don't draw the speed, obviously, so we can just ignore the speed while drawing the particle. And let's execute that. It doesn't work because, let's have a look. Right, the type definition is messed up. Let's have a look at the type definition. Oh, of course, I define a structure with the name particle. I need to follow that with a semicolon. So that should be a proper type definition now. And now we have a particle that has a speed and is being drawn. Now, okay, we are drawing the particle. Why is it not moving? Well, obviously, because we are not updating the particle. We are not moving the particle physically. The particle has a speed property, but the code is not updating its position, the x and y coordinate based on that speed property. So let's also update the particle before drawing it. And let's do the same thing. We pass a particle as input here and do the following. We do void update particle, pointer particle, and that particle is updated by saying particle x increments by particle by the speed, particle vx, and same for y, just like this. And as you can see, now we have a moving particle. Now the particle is moving off the screen, and now it gets interesting because we want to reflect it from the edge of the screen. So we have to implement collision with the wall, or collision with the walls. So when a particle, if particle, and actually we could store the particle's x coordinate in a temporary variable just so it is a bit faster to type out. So let's do float x is equal to particle x, and float y is this. And then if x is smaller than 0, then the circle is definitely beyond, well, the center of the circle, because x and y are center coordinates of the circle. Then we are colliding with the wall, and if we are colliding with the wall, then we have to reset the circle. Well, no, let me just show you how it looks like if we do it naively. We set the particle Vx component because we are hitting the left-hand wall. We just have to invert it, Vx. And that should work. Of course, it doesn't work right now because in our example, the particle moves to the bottom right corner. Let's make it move to the left-hand wall. Okay, and let's see. And as you can see, it works. However, the particle enters the wall. It does not reflect on hitting the boundary of the circumference of the circle. That's because we are just checking the position of the center of the circle here. So rather than checking the position of the center of the circle, we should check that the center coordinate plus the radius, or minus the radius, is smaller than 0. Let's try like this. If it doesn't work, we have to replace it with minus. Okay, we also need to do this. Radius r. Or let's do this. It's a bit shorter. And this doesn't work. It has to be minus r. All right. And now we are properly bouncing off this side of the wall. Right. Let's repeat that for the other walls as well. So if x plus r is bigger than, and that's why we also needed to define the width and height of the screen, is bigger than the width of the screen, then we can also invert the speed. And if y plus r is bigger than the height of the screen, then we invert the y speed. And if y minus r is smaller than 0, then we also invert the y speed. And that should give us some good bouncing movements. Let's have a look. Let's increase the speed a bit. And see how that looks like. Perfect. So sometimes if you see that the circle enters, or the center, the circle breaks through the edge of the Windows wall, and that is because the circle speed is inverted. But on hitting the wall, it could happen that the circle has already gone beyond the wall, and so ideally we should set, if the circle hits, or if the particle hits the left-hand side of the wall, then we should also update the circle's position. So in this case, we can set the x-coordinate to equal to radius. Let's check if it still works. And then we have to update that for all the other walls as well. So in case the right-hand wall is hit, let's just document this here. Left wall, right wall. Then this is width minus r. Then this is the bottom wall, or well, wall is somehow not the right term. It should be boundary. But okay, it's fine. Then the next step is to, here we can update the y coordinate, and it's height minus r. So this is basically whenever the particle is going beyond the wall, this collision detection algorithm is moving the particle back, such that the user never sees the particle going beyond the wall. Okay, let's have a look. That looks much better now. Okay, so now we have a circle that is moving. We can also, just for fun, we can visualize the frames per second in this display here, just for fun, draw FPS. There's a text drawing function called draw FPS that we can call here, draw FPS at position 5 pixels, 5 pixels, XY5. So that should be the top left corner, as you can see here. So as you can see, this is stable, running at 60 frames per second. Now comes the magic part. Simulating multiple particles. How do we do it? I would say we can do a global variable particle or particles, and that is an arrow consisting of num particles elements. Remember, we have defined this macro up here. It's just 15 currently. And instead of updating a single particle here and drawing a single particle there, we can delete this single particle and update particles instead. And that requires, of course, creating new methods. So let's do update particles and draw particles, and create some new methods. Down here, void draw, void update particles takes no arguments because we're acting on this global variable. Update particles, and then that does, what we do is we loop over every single particle. For int I equals 0, I smaller than the number of particles, I plus plus. We update, and for that we already have a method, update particle, and we pass as input particles I or particles plus I. Because particles is currently an array, so that is effectively a pointer, and then we offset it by the ith element of that pointer. Does that work? I don't know. Let's see. And then we also create a method, draw particles. That does essentially the same thing. So basically we can copy the other method that we just created, and instead of updating the particles, we can draw the individual particles like this. And let's see what happens. Syntax error. Expected semicolon before curly brace token in line 55. So let's go to line 55 right here. And of course, I forgot a semicolon. Holy crap. Okay, now it's fixed. That one's fixed as well. And now we don't see any particles. Great. Of course, why don't we see any particles? That's because we haven't even initialized any particles yet. So we of course have a global array particles here, but of course that does not hold any values. So we should have a method that initializes particles. And this one we can create it up here. Void init particles, no input arguments because we're acting on the global variable. And then we do for int I equals 0 as before, I smaller than number of particles. So for every particle, we fill some values. We create, well, we set the, no, what do we do? We get the particle, the current particle inside particles, and we set values now. So on particle, particle.x is, and now we need to give it an x value. So let's give it some dummy values first to see if that syntax is even valid. R is this, and then particle has Vx. Let's make it 1, not that, no, yeah, okay. All right, so this should be initializing every particle at exactly the same position and exactly the same speed. And it still doesn't work. Why? I'm initializing particles here. And then I'm doing this. And I think I'm not properly acting on that global array somehow. So this is the particles array. And here I'm setting values x, y, radius, vx, and vy. That should work now. And what happens if we compile this only? Let me just check for warnings. Right, variable particle is set but not used. That's already a good hint. Right, because we're... of course. Yeah, we are creating here a new variable and setting values in that new variable inside this function. Inside this function context. Of course, this does not have any effect on the global array. What we need to do is we need to access the global array directly, just like this. And then we should see a result. Let's append the collision again. And yeah, so right now what you're seeing is a single circle or a single particle moving across the screen. However, this is actually 15 separate circles or particles moving across the screen. The reason is we are just creating all of those at the same coordinates. So let's randomize the coordinates. And for that, I found that Raylib already has functions for that. And that is quite nice. So instead of using some C built-ins, we can also use those right here. So we can set a random seed and then get random values between a minimum and maximum value range. How comfortable, how useful is that? I find that super nice. So yeah, awesome. Set random seed. So let's set a seed. And the seed is important to get different random values every time, because if we didn't set a seed, then we would get the same random values with every program execution. So let's set the random seed, and it expects as input an unsigned integer. Now we could do something like this, but it must be random every time with every execution. So that doesn't work, but we can fix it by getting the current time. And the time, we can get that from time.h. And that's also how you usually seed the C internal random value function. All right. So this sets the seed, and then we can get random values using get random value here, min max. Let's try that. Get random value, and the minimum value is actually Oh, that's interesting. We first have to initialize the radius somehow using get random value, and only after we know the radius we can initialize x and y. And that is because if we set a large radius, for example 100, but set x at randomly at 0, then half of the circle will be outside of the boundary of the screen. That is not what we want. So let's set the radius of a circle between, let's make it 5 and 15. And the x coordinate can be between that particle's radius. God. I think we should even do a float radius here has no value, and then we assign a random value here. Radius is equal to get random value between 5 and 15. And then we can use and reuse radius here. So it must be radius at minimum, and the maximum value of x can be width minus radius. And same for y, get random value between 0, no, not 0, but radius and height minus radius. Otherwise, the circle would overlap the boundaries of the screen. And the speed should be a random value in x direction in this case, between 1, or no, and it can be negative, between let's make it -5 and 5. And then, same for y. Okay, let's have a look at how that looks like. And as you can see, now we have a couple of particles, and it's surprisingly working right out of the box. Oops, need to fix up my screen a bit. Let's restart. And that looks quite nice so far. And every time I execute this, we get a new random scenario. Let's try again. So every time it looks a bit different, and that is because we called this setRandomSeed function. Now, however, we're just simulating these particles, but they are not interfering, they're not colliding with each other. And that is what we need to fix. So let's do the following. Let's increase the number of particles a bit, just to make it look a bit nicer. Let's make it 35 particles. See, that is quite lively now. Awesome. That already looks super fascinating to me. But we want those particles to bump into each other. So, when updating a single particle, we make it move just like this. However, we also need to collide it with. And now the question is, if we update a single particle, can we also do the collision checking inside this function right here? Or should it be a dedicated function? So basically updates the particles, yes. But I'm worried a bit about this update particle function. It does the boundary checking and the flipping of the speeds when the wall is hit. However, when we want to check a single particle for collisions, we have to check whether it collides with any other particle. And since we are inside a loop here already, we're updating a particle and then we need to Yeah, probably it's possible just to do the following, just to append collision checking down here. If, and for collision checking is not the hard part, because there's already a function here in Raylib. Check collision circle. So here we can check whether two circles collide. Here, however, we need a nested loop for each particle, check for every other particle whether they collide. I don't really like that. So for each particle, remember this, all of this is already executed inside a loop, and then we need to check if collides with any other particle. So for int I equals 0, I smaller than number of particles, I plus plus, our regular for loop. And here I'm not even too sure if it works, but we'll see. I mean, it should work. So for every particle, check if it collides with any other particle. So here we're getting the other particles. Let's create a stack variable. Particles, particle, other particle. And that is equal to other particle is equal to particles at I. Oh. But somehow, there's another stupid issue. What if we're accidentally comparing a particle with itself? Then obviously it will collide with itself. That will be a problem. I'm not sure about this. Now let's create a separate method. Let's call it collide all particles. And the update particles method collides with walls, and the collide all particles method collides with other particles. All right. Then let's create that method. Void collide all particles, and here for int I equals 0, I smaller than number of particles, I plus plus, we do the following. We do another loop for every particle, check whether it collides with any other particle. And here you already see that it's square complexity. Sorry, my phone tells me something. I need to stop a recording from my earlier running session. Alrighty. And there we go. All right, let's continue. Int j equals 0. Yeah, so we have a squared complexity. So with the number of particles that we simulate, the complexity rises quadratically. Do we say quadratically? Geometrically. I've been out of university for too long. All right, and then we check if I is equal to j, return, because then we don't need to check. Don't collide a particle with itself, right? If I is not the same as j, then we get the particle that we are looking at, P1 and P2, and P1 is equal to particles at I, and P2 is equal to particles at J. Okay, I think this is how we should do it. Right. And let's still check if the application runs. No, it does not run because of a syntax error in line I113. Oh, we already have coded 113 lines of code. That's quite a bunch for that short time. Okay, so it's still running, not colliding, because in our collide all particles method, of course, there's no logic yet. So here we are fetching the particles, and now comes the interesting part. Let me just have a sip of tea. All right. Now comes the fun part. Everything that we did so far was simple. It was just moving circles across the screen using ready-made library methods. Now, for the collision behavior, we don't have any library methods. Well, we do have library methods for detecting a collision. Yeah, and of course we need to make use of them. So let's do that. Bool check collision circles. And that checks a collision between two circles. Obviously, it returns true if two circles collide. That is a circle represented by center 1 and radius 1, and a second circle represented by center 2 and radius 2. All right. So we need to check if those particles, if they collide. So if, or maybe let's store it first in a Boolean. Collide is equal to check collision circles. And then we need to compare the center points and the radiuses. So let's get a vector 2. Center 1 is equal to P1x P1.x and P1.y. Same for center 2. And the radiuses, we can get them dynamically here. So C1 and radius is P1.r and C2 and radius is P2.r. So this returns if something collides. If the particles collide, then we do something. Then comes the really hard part. Here comes the hard part. I'm manifesting a hard life here. Okay, maybe we should check if the collision even works. So here we can printf collision happened, and just like this. Now we can see if collisions even happen, if they are detected. No, somehow it's not printed to the console. Why? Oh, that's interesting. Why is it not being printed to the console? Maybe because I cannot use a Boolean like that. Maybe because in C there's inherently no Boolean. And wait, let me just check the warnings in my code. Usually the warnings tell me all the answers I need to know. There are the warnings. In function collide all particles. Implicit declaration of printf. Okay, it should be fine. I think it has to do with the Boolean usage there. So let's include standard.io. And there are no printouts to the console. That means that the collision printout that this if case does not trigger. So we maybe need to explicitly compare collide to true, and maybe only then it works. No. What's wrong? That's the center point. That's another center point. That's the check collision circles method. And it's comparing vector 2, center 1, float radius 1, vector 2, center 2, float radius 2. Check collision circles. Okay, then let's print f. Let's just print f all of that right here. And that is not printed either. What the hell? Are we entering this if case all of the time? For int I equals 0, I smaller than number of particles, I plus plus. Then for int j equals 0, j is smaller than number of particles, j plus plus. So what if I print f here? I is equal to this and j is equal to this. And then I do I and j. Let's print them. And that, why are they, wait, what the, why are they always 0? Why am I not properly looping? I'm doing I++ and j++ here. What the hell? This is really challenging my programming knowledge right now. I'm calling I++ right here. If I do int I, if I do this, does this change anything? No, shouldn't. Of course it doesn't change anything. No, seriously, that's very, very, very weird. Collide all particles is called here. And then if I equals j, then we return. So the first iteration returns. Damn it, oh my god. We return the entire method, but we should just break the loop. Of course. There it is. Okay, yeah, so I confused return and break. Oh my god, that one was a bit tricky. Okay, so let's remove the printfs here and let's try again. And we have a bunch of collisions printed to the console. So collide seems to be working. All right, that was a good bug fix. It was very valuable to have fixed right now rather than later. All right, and now comes the hard part. So let me just open a drawing application here. Just give it a second. Let's create a new image. Black. All right. So we have a sphere or a circle. Of course, it should be white. Just like this. And another circle. Just like this. Can I move it? No. And they collide. Oh, they collide like this at first. Then both of those have center points. Let's say those points right here. And then initially they overlap because they are moving into each other in discrete time steps. So we cannot detect whether exactly the edges here are colliding or whether they are already overlapping. I think the collision method returns true if they are already overlapping. No matter how much. So if we reach that true case, that means they are overlapping already. And by just some common knowledge, we all know that this does not exist in real life. Right? Two particles cannot overlap like that, at least not in classical physics, as far as I know. So we need to draw them apart again. For that, we need to move every single particle outside. Let me just pick another nice color. How can I do that? Here, let's get this color. We need to move this here and this particle there. How do we know the direction? The direction is implicit in the connecting line between the center points, as you can see here. And maybe we should even make that a different color. All right. So there's this line that connects the center points, and that is the so-called collision normal, as far as I know. And that line, that is, of course, very easy to find out. Let's assume that this is circle 2 or particle 2 and this is particle 1. Then the collision normal is just the difference between the x and y coordinates. Right. So we need to, step 1, move apart two colliding circles or particles. To do that, we need to find the collision normal. And then we need to move the circles apart. By how much? Well, imagine we draw a line here. Just like this. This is the line that goes through the cross sections here. And now we need to move each circle just this tiny bit apart. Just like this. And then this section here as well. And this is the normal vector. Let's call this n, multiplied by this cross section. Let's just call it cross section. It's this distance right here between the overlapping edges divided by 2, because one just has to move out by this half and the other has to move out by this half. All right. So find the normal vector. Okay. We get the difference between the center points. C1 or P1.x, doesn't really matter. P1.x minus P2.x. And that is nx. And then we have to normalize it to know just the direction without the absolute value. Let's call it distance x. And that's a floating point number. And the distance y is also a floating point number, of course. It's the same thing as here. And now the next step is, this is basically the distance vector between both center points. And if we normalize it, we get the normal vector, and that is equal to dx divided by the square root of power dx to the power of 2 plus the power of dy to the power of 2. So basically we take the x component. This is the absolute value of d. Actually, we can store that in another variable. Abs d is equal to this. And then we can divide dx by abs d. And ny is the same thing. It's dy divided by abs d as well. All right. So now we have the direction. It's nx and ny, and that points from one center point to the other center point. And now we can move apart the particles using nx and ny. But how much? How much are they overlapping? That's the question. Here I named this normal vector n, and we multiplied it by this overlapping section. Well, the overlapping section definitely has to do with the center points, obviously, and the radiuses. Right, it must be the center point here. Let's consider this 0. And then this center point has a distance, d. And we know that the intersection must be exactly at the middle. No, it is not necessarily located at the middle of the intersection here. Of this distance vector. So we know d minus r1 plus r2 maybe. So d minus r1 is this. This is no. If we have consistent naming, then this is r2. So r2 and then here plus r1. Effectively, this is d minus, and then the difference between the radii, r2 minus r1, like this. And then we divide all of that by 2. I think that might work. All right. Let's create a new float, overlap, and that is equal to d minus r2. That's the center point, of course. We need p2r, right, that's the naming, minus p1r, divide that by 2. Or no, that's the overlap, that's the full overlap. And then we move out circle 1, so p1 dot x equals, and now we get the old p1.x and we increment it by nx, that's the normal vector, in x, and that's the x component of the normal vector, with the overlap. No, that cannot be the case. We need an overlap vector, don't we? No. No, that might, no. Let me just try this. I think it might work. Let's see. So error expected parenthesis before semicolon, line 93. Line 93 is here. Expected parenthesis, right, correct. Now, line 97, expected parenthesis, of course. And actually we can remove parentheses here. NX undeclared, 94. Right, because that's a new floating point number. And now we get a couple of warnings. D and an error, D is undeclared. What's D? It's called absd in our case. Where do I use D? There I use it, absd. And this doesn't seem to do anything. And that's quite weird. Why doesn't this do anything? It doesn't do anything because I just compared the particles on the stack, but I need to access the global particles here. I need to update the properties of the global particles. So let's access particles at index I.x. And here particles at index j.x. And we need to multiply that with overlap divided by 2. Same thing here. And then we do the same thing. Wait, what the hell did I code here? No. So this might be correct. This is updating the first particle, and let's update the other particle, but in the other direction. So let's do minus equal to, like this. Or instead plus equal to, and then negative nx, just to make that more explicit. And as you can see, whenever two particles touch each other now, they are behaving quite weirdly. Looks awful. And I don't know if it's correct, but I really don't know if it's correct. But at least we see some interactions. I don't think it's correct. So let's review the code a bit. So dx is p1x minus p2x. dy is p1y minus p2y. The distance is this. The normal vector is this. That should be correct. Then this is an overlap. The overlap is the distance minus p2 radius. Let's have a look at our sketch again. P2 radius. Okay, let's just consider this line. This is the full collision line across which we're looking at. Then let's say this is radius 1. And let's say this is radius 2. R2, and this is R1. All right. What's the overlap? Overlap is equal to D minus R1 plus R2. Yeah, so that was correct. That's the overlap. But maybe I mixed up something here. Maybe we have to do P2R minus P1R minus overlap. Something like that. No idea. Let's have a look. This one looks... Does it look better? We see that the particles are now somehow colliding into each other. Sometimes there's some weird behavior, but that is, I think that's normal since they are not reflecting each other. Oh no, this one is behaving very weirdly. Those are two particles stuck inside each other, I think. Nx and y minus nx minus ny. Wait, what the hell is that? I define the overlap in relation to the overlap itself. This should of course be abs d here. And then also, this should be well, we have to add up R1 plus R2 and then subtract the difference at the distance to get the overlap. Let's try now. Is it? Oh, I think it looks better now. So the circles are... Wait, if I increase the size of some circles, maybe you can see it better. So let's make the circle radius a random value between 5 and 20. So you can see that they are moving each other out of the way and they are not intersecting with each other. They are not overlapping. That's perfect. Okay, that's very good. So now, next step. Okay, we move apart two colliding particles. Now we need to figure out how the hell do two particles reflect each other. So, yeah, let's start a new sketch here. We have a circle here and another circle here. Let's do this such that they don't overlap. Or maybe, yeah, that's too big. this is a circle, and this is another circle. How do they reflect? We know that there's a line connecting both of the center points. Now, the next step well, basically now it's as if they are just bouncing off a wall. And the wall is tilted like that. So imagine that the first circle is moving like this. The first circle is moving like this, and the second one is moving also like this. And then it's like they're just bouncing off that wall, somehow like this. Right? How do we exactly find that angle? Well, we need to consider that skewed wall angle here. And we know that this so-called tangent here is perpendicular to our distance vector between the center points. So this is perpendicular. That means if that distance vector has some properties, let's say distance is equal to dx and dy, then the tangent vector will be d minus dy dx. Why is that? Well, that's because the scalar product between dx and between d and t must be zero, because if it's zero, then that means that two vectors are perpendicular, and that means the scalar product here is dx multiplied by minus dy. So dx multiplied by minus dy plus dy multiplied by dx, dy multiplied by dx. Oh, you can't see what I'm drawing here. dx. And that is always equal to 0. And that is because we flipped those entries in the d vector intelligently. Yeah. Why does the scalar product need to be 0? That is because the scalar product is, if we do d multiplied by, or dot product with t, then it's the absolute value of d multiplied with the absolute value of t multiplied with cosine of phi, and phi is the angle between two vectors. So if we have, for example, let's say this is an arbitrary vector v1 and this is an arbitrary vector v2, then this right here is phi. Okay? So between the distance vector and the tangent vector, if the cosine, and the cosine is only ever, well, no, forget about it. Cosine, we want phi to be 0. We want this angle to be pi divided by 2, because that is, let me just write that here. We want this angle to be phi ought to be pi divided by 2, because cosine of pi divided by 2 is 0. And this means that this part will be 0. And this means that d dot product t will be 0. Yeah, so that's effectively the logic. And that's why we can flip those entries like this. All right. And no, it's not natural to know this. It's not natural to know this. I had to look it up before the video. So let's try. The tangent vector is therefore equal, or the tangent vector's x component, float tx, is equal to minus nx, because we want the normalized tangent vector. We don't want the, I've messed this up. It should be the n. It should be the n vector, because I want a vector of a length 1. Because we just want the direction, we don't want an absolute length of this full wall here. Then float ty is equal to, no, this must be minus ny. This is nx. This is the tangent. Well, normalized tangent vector. And then we can figure out, because we now know what the tangent vector is, we can figure out if we project this velocity here onto this tangent vector up here, how much velocity will be reflected into this direction. So effectively, let's just say we have an incoming vector. This right here is our tangent. This is the wall. And then we have an outgoing vector. We don't care about well, no. What we do care about is, in this case, let's just assume this is a regular x-axis. Then we would only we wouldn't care about the y component of the speed. We would only care about the x component of the speed. And then we would be able to just flip the y component. And similar to that, we would, in this case, in case we have a skewed tangent vector, we would care about only the speed component that would correspond to x in this case up here. But in this case, it's a skewed x because it's a new coordinate system in that sense. So basically, we are projecting a new component here on that tangent vector, and we can do that with the dot product as well. So we basically need to get the effective x speed in this new coordinate system. And then the y component, we can just flip it. Or rather, we can just flip it, I think. So effectively, the new speed, how should I call it? V1x dash. This is the new speed, the updated speed. Or particle 1, no, V1x dash is fine. Is now the dot product tx multiplied with what's the original speed? Did I already extract it up here somewhere? No, I didn't. Right, we haven't even done anything with speeds so far. So particle 1 Vx multiplied with Tx plus no. I'm computing a dot product here. A dot product is always a single number. Right. And this is v1x dash is p1.vx multiplied by tx plus p1 vy multiplied by ty. That is the dot product. No. Something. I'm thinking of something wrongly here. I've basically found out this length, I think, if everything is correct. So this length right here. But I need the new direction. And I think that's the new... Wait. That's... Right, that's just the speed v1x. Probably. Oh god. And v1y is just... But I also need to... that might be the dot product, with, not with the tangent vector, but with the normal vector. Wait, if I do this, p1.vx multiplied with the normal vector plus p1vy multiplied with the normal vector. Oh, no idea. But it feels correct. And then the next step is to assign particles at i.vx, this new speed, right? v1x. And vy is v1y. And the other particle gets v2x and v2y. But here, what's the difference? Particle 2vx and particle 2vy. And particle 2vx and particle 2vy. Oh, I'm almost 100% sure that this will look not the way I'd like it to look, but there's a small chance that it still works. Let's see. Yeah, no. This is definitely wrong. Oh my god. Okay, this is completely wrong. So, this is the tangent vector. This one should be correct. Then, and it should be correct because we know through the law of the scalar product that this results in a zero value if we dot product it with the normal vector. That should be fine. It's just this thing. So what I'm struggling with right now is this. Let's just, redraw something here again. So we have a tangent vector t. We have some other vector. Let's call that other vector. Or actually, let's draw it down here. That's, for example, v1. Then the dot product returns exactly this value here. It returns this distance because we know that the absolute value of t is equal to 1. So this is the distance that is returned. And actually, Now we know this component here. This is basically v1 projected onto t. And now how does v1 reflect here? Holy crap. v1t, and then, so let's say this is the tangent, then we have a circle moving in at v1, and then it's reflected like this. So we know that v1, this is the absolute value of this v1 of the tangential speed is v1t. Right, this is the tangent component. Let's call this t1. And this, let's call this n1. Right. This is p1vx multiplied by tx plus p1vy multiplied by ty. And this is t2, and this is n2. So those are now the tangent. This is not the tangential speed component of the speed vector, and this is the normal component of the speed vector. Right, and I think they are in the wrong coordinate system right now. So this is not quite correct. We need to translate those into our original coordinate system, I think. But how? Where did we make the transformation? We made a transformation here. No. Yes, we did. I think we need to do particle, the first particle, Vx is now T1 multiplied by Vx maybe? No, I'm just guessing. This is probably completely wrong. N1 multiplied by Vy. Oh, this is wrong. I still want to see the result. Oh. No, let's forget about seeing the result because I know it's wrong. This is the tangential component. This is the normal component. So effectively, currently we have a coordinate system. This is x and y, and now we have some skewed coordinate system inside. For example, like this, and this is the normal, and this is the tangent component. And we know as a result, this is the new vector here. And now we need to convert that to this X and Y representation again, I think. So what we can do is we can we could technically do another dot product with 0, 1. Oh. Wait. T1 multiplied with P1 Vx plus, and maybe it is correct. Wait, T2 multiplied by P2 dot, no, P1, what am I doing? N1 multiplied by P1 Vy, T2 multiplied by P2 Vx No, completely wrong, as you can see. Oh my god. Wait, we know that the tangential component stays the same. The normal component is... Isn't it flipped somehow due to the reflection? No. How the hell do two particles reflect each other? Normalized tangent vector. That should be correct, right? This should be correct. And then here, T1 is equal to Vx multiplied by Tx. And that error is right. Here, there's something wrong. I multiplied with nx instead of ny for the y component. Let's see how it behaves now. Still horrible. So P1 Vx multiplied with Tx, P1 Vy multiplied with Ty. P1 Vx multiplied with Nx, P1 Vy with Ny. So all of this is Y, all of this is N. Right, and one more thing, I think we have to swap the the normal components of each mass, because when one circle hits into another circle, then the normal component of that speed, let's say this is the speed. Let's say this is the speed. It has some normal component relative to this tangential vector that is reflected back, and it is reflected by exchanging it with the normal component for this mass's normal vector. Let's try again. So T1, N1. So, and here N1 depends on the P2 Vx and P2 Vy. That's essentially what I wanted to say. And it still looks horrible. Oh my god. And that might be because here I put the minus signs, but those are wrong. No. Why is it not even getting a bit better? So the tangential components, they stay basically constant in both, well, not constant, but they don't depend on the other mass. The normalized components are flipped. And maybe here I have to put a minus, or no. Maybe not. What if I put a minus here? By the way, that's not a reliable algorithm to doing maths. You're not guessing your way through to the solution. Holy crap. Vx, Vy, Vx, Vy, P1, P1, P2, P2. So the overlap worked. There must be some deeper issue here now. It's not just a simple coding bug. Why am I multiplying T1 with Vx here? But then I'm multiplying N1 here with Vy. What if I do T1 and no, or T2 here and one just like this. Let's just shuffle around a couple of variables. N1, T1, N2. No. What else can I do? T1, T2, N1, N2. No. Oh god. I just read up a small bit of vector stuff, just enough to maybe get this right now. We need the V1 tangential component. Forget about those. Or V1x? No. And here we have to do V1. The tangential component is equal to what is V1? It's P1 Vx multiplied by Tx plus P1 dot Vy multiplied by Ty. Same for V2T. Then float V1 normal component is P1 Vx multiplied by not Tn, Nx plus P1 dot Vy multiplied by Ny. Same for P2. And then the tangential components, they are flipped because the impulse is exchanged. No, the normal component is exchanged. So let's do particles I V1 n no Vx equal to V2. Okay, wait. I'm a bit confused, as always. And so now what is the speed here? The x speed is V1 is P1 Vx and those are just absolute values. So now we get no. The original speed and multiply with no. I'm not sure. Vx, the speed in x direction, is equal to, well, is it this speed or this or this or this, or is it something completely different? I don't get it. I think it might be here we get the original x and project it onto the tangential component. That's the tangential speed. Then those are somehow flipped as far as I know. The normal speeds are flipped. V flip is equal to V1n. Then let's set V2n to V1n and V1n to V2n. Ah, no. That means Vn flip must be V2n. So I'm just exchanging values here. What if I do this now? V2t and V2n. Oh, this looks, oh, it doesn't look good, but it looks better than before. Some reflections look correct, others don't. Wait, so I think we're doing something right here. What if I replace that with V1n here? Oh no. V1 or V2t? Is that correct now? I don't think it's correct, but well, we're doing something correctly. It looks like momentum is being lost in this simulation somehow, but oh my god, it looks unrealistic. But something's correct. And now I just need to know how to properly assign those values here. What if we don't do this flip? Oops. Doesn't look too bad either. So we flip the normal components, then Vx, Vy, V1n, V1t, V1, V2n, no, V2t, V2n. I would say this. Yeah, no. Somehow it's right, but then it's not entirely right. Why do they stick together sometimes? Maybe it's because I am doing something wrong. Maybe, yeah, one issue might be that we're checking the same particles multiple times. So if I is 0 and j is 1, then we're checking particle 0 and 1. And then later when I is 1 and j is 0, then we're checking the same particles again. Shouldn't do that. So how can we change it? For I equals 0, I plus plus, for example, for particle 0, we could start with j equals 1 or I plus 1. Oh, yeah, maybe that makes sense. So for particle 0, we check with all other particles. For particle 1, we check with we're missing particle 0 then. But it was already checked before. What about particle 5? Then we start counting at particle 6 here. So we compare particle 5 with 6, 7, 8, 9, 10, 11, etc. But what about particle 5 and 4? Ah, that one was already checked before. Maybe this already works. Wait. And well, it looks like the collision still works, so I think the checking is now a bit optimized. Something is still very, very odd. I think we're close. We are very, very close. The X component is V1T. I'm actually convinced. The normal components, they are flipped. Ah, of course, that's an issue. I assigned the value of V2N here, and then assigned that same value, which I just overrode here, to V1N, but that's what the point of that variable. I should pay more attention to the warnings, because if I had read the warnings, now I'm sure it's part of the warnings, and yes, there it is, unused variable. We should check the warnings more often if something doesn't work. So let's check the code now. Wait, I need to include math.h as well. And now let's compile. We have no warnings. Guys. Yes! It's working, guys. Oh my god, we have a working particle simulation here with particles of different sizes, of course, which looks a bit unrealistic. Let's make them all the same size. Oh my god, I'm so... well, my heart just became lighter. Let me put it like that. Let's just all make them a bit... let's just give them a similar size. Let's simulate many more particles. Let's simulate 100 particles. And let's also define the particle color. Let's quickly have a look at the Raylib available colors. I think they are available down here. Let's use... Wait, Raylib colors. I'm a visual guy. So let's use sky blue. No. Sky blue. No. Magenta. Color. Oh, we can also use this. Oh, that's good. Okay. Then let's go to draw particle. Color. And then we can define our own color. 255. Let's do 255. No, 0. Ah, it didn't compile. Oh god. No, didn't want that color. How about this one should be white, right? No, because I didn't compile. Let me append the compilation again. Yeah, okay, actually white is fine. What about red, green, blue? Let me just remove the red part. Ah, no, that's what we just had. Wait. Or this part? Ah, that's nice. Okay. I don't know which one I prefer, honestly. I really don't know. What if I give it a bit brighter value? Something like that. Let's make it almost white. Oh, let's keep it white. Oh man. And yeah, let's just keep it white. So white and maybe one more interesting thing that we could do in this video would be to add some gravity. And we can do that when we are updating individual particles and we can define here, define gravity. Let's just make it 1. And gravity is a force that changes the velocity of the y component. The y component of the velocity. So particle Vy is incremented by negative gravity. No, positive gravity, because the y coordinate is pointing downward on the screen. And that looks horrible. What the hell? Gravity. And then we also have to add some dampening to make this more realistic and also lose some of the... What is the term again? Momentum. So we have some gravity now. We can also make it 0.01 or something like that. And then gravity... And on collision, if there's ever a collision, we do bool collision is false. If there's a collision, then we set collision to true. Also down here. And if there's a collision, if collision is true, don't think we need to explicitly state that the collision is true, then we lose some of the velocity maybe. Particle dot Vx is equal to Vx, arrow operator, is reduced by 10%. Same for Vx. That's very little gravity now. And also, of course, we need to do that when colliding with other particles. So it's not a purely elastic reflection. Oh my god. It's losing some force. Particles at I dot Vx. And here the collision variable is called collide. collide particles at index I dot vy is this, and same for particle j. All right, and as you can see, the speed is slowing down a bit, and over time all the particles are falling down. The gravity is very, very low, as you can see. So let's make it a bit higher so we're seeing results faster. Also, the 0.9 might be a bit harsh. So let's call that a function that's called a constant that's called the dampening factor. And let's make that 0.98 or something like that. And let's search for 0.9, replace that with dampening factor, just like this. Same thing here, dampening factor here as well. Dampening factor. Dampening factor. Okay. And now it must work. And as you can see, we have a couple of... Oh my god, this looks super realistic. I love it so much. This is so awesome. This is so freaking awesome to me. I never thought I would be able to code such a thing. Let's try 400 particles. Make all of them a bit smaller, and let's give them all a larger speed range. So let's give it a constant speed here that we are going to define also globally. That's the speeds which we can choose from. Radius can be 5 to 10, for example, and then let's define speed, and this is basically the maximum speed. Let's make it 15, and let's see. And as you can see, we have a ton of particles, and it runs smoothly, and all of them are settling over time. Oh my god, this is such an awesome result to me. I'm speechless. And of course, at some point, the performance will deteriorate. So for example, if we do 800, I can imagine this will run significantly slower. No, it's still fine, actually. And this looks like dust settling over time. This is so nice. Oh my god. What about we're making this 2000 particles? Still works, but now the screen is full, and I'm surprised it still works. But there must be, it's working at 30 frames per second, so we're in the range where the performance significantly deteriorates now. Right, so because this is just not optimized to run for very large numbers of particles, because then you would have to divide the window into grids and check whether particles are inside your grid, and then only compare the neighboring particles who are also inside that grid's cell for collision. All right, but for this video, this is a super nice result. So we can, without problem, simulate 500 particles at 60 frames per second. The particles are bouncing into each other and gravity slowly pulling them down over time. Perfect. I have nothing to add. If you want to support this channel, consider becoming a Patreon. Have a look at the description to get my exact dev setup. And also, I highly recommend to you guys Proton VPN. I'm always using it whenever I'm online to stay anonymous and to ensure that no internet service provider is tracking my identity. All right. Check out the description. I have a couple of very, very useful links there for you. All right, and let's have one last look at the simulation. And then let's see you all again next time. Bye-bye.